We've just taken a look at the what and the why of system-on-chip design, including some great real-world examples. Now, we're going to shift our focus to a more evaluative topic, as you can see highlighted here, the advantages and limitations of SoCs. It's really important for any engineer or designer to understand the trade-offs involved with any technology. Nothing is perfect for every single situation. So, in this next section, we're going to do a deep dive into both the pros and the cons of the SoC approach. First, we'll explore all the reasons why SoCs have become so dominant, especially in mobile devices. We'll talk about gains in performance, power savings, and cost reductions. Then, to make sure we have a balanced understanding, we'll look at the other side of the story, the limitations. We'll discuss things like flexibility and the challenges involved in designing them. By the end of this section, you'll have a clear idea of the strengths and weaknesses of using a system-on-chip. Now that we've seen what a system-on-chip is, let's talk about why this approach is so powerful. This page breaks down the main advantages of using an SoC. First up is higher performance. Why are SoCs faster? There are two main reasons listed here. The first is less propagation delay. Think about it this way. If you need to pass a message to someone, is it faster to hand it to the person sitting next to you or to walk across a large room to deliver it? It's faster when they're close by, right? It's the same for electrical signals. On an SoC, all the components are packed tightly together on a single piece of silicon. The wires connecting them are incredibly short, so signals travel almost instantly. This is a huge improvement over a traditional circuit board where signals have to travel much longer distances between separate chips, which introduces a delay. The second reason for better performance is less gate delay. A logic gate is a basic building block of a processor, and gate delay is the tiny amount of time it takes for that gate to process an input and produce an output. The slide says internal transistors have lower electrical impedance. You can think of impedance as a kind of resistance to electrical flow. With lower impedance, it's easier and quicker for signals to switch the transistors on and off. This means the fundamental operations inside the chip happen faster, leading to overall higher performance. Next, we have power efficiency, which is absolutely critical for mobile devices like our phones. SoCs are incredibly efficient for two key reasons. They require a lower voltage. Signals traveling inside the chip don't need much power, typically less than 2 volts. But to send a signal from one chip to another on a motherboard, you need a stronger, higher voltage signal, often over 3 volts, to make sure it arrives clearly. By keeping everything on one chip, we avoid using that higher, power-hungry voltage for communication between core components. The second reason is less capacitance. The long wires between separate chips act like tiny batteries that have to be charged and discharged every time a signal is sent, which wastes energy. The microscopic connections inside an SoC have much lower capacitance, saving a significant amount of power. The third advantage is a lighter footprint. This one is quite intuitive. When you integrate a processor, memory, and other peripherals onto a single chip, you eliminate the need for many separate components and the large circuit board needed to connect them all. The result is a much smaller and lighter final product. Think back to that picture comparing a full motherboard to a single SoC. That says it all. Then there's higher reliability. In any electronic system, one of the most common points of failure is the physical connection between components, the solder joints. By putting everything on one chip, you dramatically reduce the number of these external connections. Furthermore, sealing everything inside a single chip package protects the sensitive circuitry from the outside world, from things like dust, moisture, and electrical interference. This makes the whole system much more robust and less likely to fail. Finally, we have low cost. Now, you might think that designing something so complex would be expensive, and the initial design cost is indeed very high. However, the advantage comes from mass production. Once the design is perfected, you can manufacture millions or even billions of these chips at a very low cost per unit. This economy of scale makes it much cheaper than producing and assembling multiple different chips onto a circuit board for every single device. So, SoCs give us devices that are faster, use less battery, are smaller, more reliable, and cheaper to produce in large quantities. It sounds almost perfect, doesn't it? But as with any engineering decision, there are always trade-offs, which we'll explore on the next page. While we've just talked about the many fantastic advantages of systems on a chip, like their high performance and low power consumption, it's also really important to understand the other side of the coin. Like any engineering decision, choosing to use an SoC involves trade-offs. This page outlines the main limitations you'll encounter. First, and perhaps most obvious to an end user, is less flexibility. Think about a standard desktop PC or a laptop. Have you ever upgraded your computer? Maybe you added more RAM to make it faster, or you swapped out the graphics card to play newer games. You can do this because those components are separate, modular pieces that plug into a motherboard. An SoC is fundamentally different. All those components, the processor, the memory, the graphics, are permanently integrated or etched onto a single piece of silicon. This means that once the chip is manufactured, its hardware configuration is locked in forever. You can't upgrade the RAM or the processor on your smartphone because it's all part of one inseparable SoC. The second major limitation is that SoCs are typically application-specific. Because the hardware can't be changed, it has to be designed with a very particular job in mind right from the start. For example, the Apple A series chip in an iPhone is meticulously designed to handle tasks like running iOS, processing photos from the specific camera it uses, and managing the display. It's highly optimized for that one device. But because of this specialization, you couldn't take that same chip and use it effectively in a different product, say a network router or a smart TV. It's not a general-purpose tool. This high degree of specialization is what makes them so efficient for their intended task, but it also makes them very inflexible for anything else. Finally, we have the challenge of complexity. This is a huge factor from an engineering perspective. Designing a system on a motherboard, what we call board-level development, involves selecting pre-made components and connecting them. But designing an SoC is like building an entire city on a tiny piece of sand. It requires an immense level of expertise in many different fields, from digital logic and verification to physical layout and power management. As we saw a few slides back when we discussed the design productivity gap, our ability to create complex hardware has often outpaced our ability to design it efficiently. The process is incredibly expensive, and a tiny mistake can be catastrophic, potentially requiring a complete redesign and refabrication, which costs millions of dollars. This is why SoC design requires highly advanced skills and is a far more difficult undertaking than simply assembling components on a circuit board. Now that we've talked about the concept of a system on chip, you might be wondering how it compares to other terms you've likely heard, such as processor and microcontroller. It can be a bit confusing because all three are fundamentally built on a single chip package, but they have very distinct roles and capabilities. This page helps us clarify those differences. Let's start with the first item, the processor, which we often call the CPU, or Central Processing Unit. Think of the CPU in your desktop or a laptop computer. Its primary goal is performance. As the slide says, it's designed for general-purpose computing. This means it's made to run complex software like operating systems and demanding applications. To achieve this, it might have a single powerful core or, more commonly now, multiple cores. The design philosophy behind a CPU prioritizes raw computational power, often without strict constraints on its size or how much electricity it consumes. However, A crucial point about a processor is that it can't function alone. It's like a powerful car engine. An engine is amazing, but by itself, it can't get you anywhere. It needs to be part of a larger system, a car with a chassis, wheels, and a fuel system. Similarly, a CPU needs to be placed on a motherboard and supported by external components. It requires separate chips for memory, RAM, and various input-output controllers, or I/OS, to communicate with things like your hard drive, USB ports, and display. So, a processor is the powerful brain, but it relies on an external support system. On the other hand, we have the microcontroller, or MCU. A microcontroller is fundamentally different. If a CPU is just the engine, an MCU is more like a complete go-kart. It has the engine, the frame, the wheels, and the steering all in one small, integrated package. As you can see on the slide, an MCU typically contains a processor core, usually a less powerful one than a desktop CPU, but it also includes its own memory, both RAM and storage, basic I/O ports, timers, and other essential peripherals, all on the same single chip. Because everything is self-contained, MCUs are not designed for high-performance computing. You wouldn't run Windows on a typical microcontroller. Instead, their main purpose is for basic control in what we call embedded applications. Think of the simple computer inside your microwave, your digital thermostat, or a TV remote. These devices perform specific, dedicated tasks. They are optimized for low cost and low power consumption, making them perfect for control-oriented jobs. So, the key difference to grasp here is between a high-performance, component-based approach, the processor, and a self-contained, control-focused approach, the microcontroller. This naturally sets the stage for our main topic. Where does a system-on-chip fit in this spectrum? As we'll see on the next page, an SoC really bridges the gap between these two concepts. On the last page, we looked at processors and microcontrollers. Now, let's talk about the third and most complex category, the SoC, which stands for System on Chip. Think of an SoC as the ultimate all-in-one package. While a microcontroller is a simple system on a chip, an SoC is a much more powerful and complete computer system on a chip. First, let's talk about processing power. An SoC can have a single processor core, but more often, it features multiple, highly powerful processor cores. This is a big step up from the typical single, less powerful core you'd find in a microcontroller. This multi-core setup allows it to handle many complex tasks at once, just like a modern desktop computer. Next, an SoC packs in much larger memory blocks and a wider variety of I/OS and other peripherals compared to a microcontroller. It's not just about having more memory, it's about having the right kinds of interfaces for advanced devices. And this brings us to a key feature of SoCs. They are normally integrated with other very powerful, specialized blocks. For example, a GPU, or graphics processing unit, is essential for handling the complex graphics in games and high-resolution video. A DSP, or digital signal processor, is optimized for handling signals like audio or processing camera image data. Many SoCs also include dedicated hardware for encoding and decoding video. A standard processor or microcontroller simply doesn't have these specialized, high-performance units built in. Because of all this integrated hardware and processing power, an SoC is usually capable of running a complete, complex operating system. We're talking about the operating systems you use every day: Windows, Linux, iOS, and Android. A microcontroller, in contrast, typically runs much simpler software or a specialized real-time operating system. The ability to run a major OS is what allows for a rich user experience with a graphical interface and multitasking. So, where do we see SoCs in action? They're mainly used for advanced applications. The chip inside your smartphone or your tablet is a perfect example of an SoC. It contains the CPU, the GPU, the memory controllers, the Wi-Fi and cellular radios, and all the other components needed to make the device work, all on one tiny piece of silicon. To summarize the difference, a processor is the brain. A microcontroller is the brain plus some basic organs for simple control tasks. An SoC is like the entire nervous system, sensory organs, and more, all packaged together, ready to power a complex device like a phone. We've discussed the theoretical advantages of SoCs, and a major one is power efficiency. This page shows us where that advantage has had the biggest impact in the real world of commercial products. SoCs are absolutely essential for the mobile devices we use every day. Because they are so power efficient, they've become the standard for smartphones, tablets, and even digital cameras. Think about it. These devices need to be powerful enough to run complex apps and process high-resolution images, but they also need to run on a small battery for many hours. This balance of performance and power saving is exactly what SoCs provide. This huge demand has led to a large and competitive market. There's what the slide calls a large ecosystem of design companies, all creating their own SoCs. You'll likely recognize many of these names. We have Snapdragon, which is made by Qualcomm. If you've used an Android phone, there's a very high chance it had a Snapdragon chip inside. Then there's Tegra by NVIDIA, a company famous for its graphics technology. NVIDIA's Tegra SoCs are often found in devices where graphics performance is key, like the Nintendo Switch gaming console. Of course, there's Apple, which designs its own A-series chips, like the A14, A15, A16, and so on, exclusively for its own products like the iPhone and iPad. And we also have Texas Instruments with its OMAP family of SoCs, which were very popular in many early smartphones. Now, here's the most important point on this slide, the one that connects everything together. What do most of these different chips from all these competing companies have in common? They use ARM-based microprocessors. So, why has ARM become so dominant in the mobile space? It comes down to that critical trade-off we just mentioned, delivering high performance with less power consumption. ARM's processor architecture is famously efficient. It allows companies like Qualcomm and Apple to build chips that are incredibly fast but don't quickly drain your device's battery. This combination is the key to the modern mobile experience. This is a really important concept to grasp. ARM Holdings, the company, doesn't actually manufacture chips. Instead, they design the processor architecture and license this intellectual property, IP, to other companies. These companies then integrate the ARM processor cores into their own unique SoC designs, adding their own custom components like graphics processors, GPUs, memory controllers, and modems. This is why we see so many different brands of SoCs, but most share a common ARM foundation. In the following slides, we're going to take a closer look at a couple of these specific commercial SoCs to see what they actually look like on the inside.